So I know Taylor's here, right? And is it Taylor?
Yes, sir.
Taylor? Huh? Okay. And remind me, I got Alexis? Okay, awesome. Okay, then let me back off. Kaylin or Taylor?
Kaylin.
Kaylin, that's what I thought. And then I thought you said Taylor. I thought you were giving her name. I thought, okay, wait. Okay. So I'm going to circle that because I'm not sure she's what we have. So we got 4 here. Double the class size. Way to go. Okay, we are recording. And as I was telling the others, I want to go over a whole bunch of stuff about how to wrap up the term, but I want to wait till more people get here. Otherwise, I'll be saying the same thing over and over every time new people come in. So before anyone leaves today, be sure to tell me, I got to go so I can go over all the end of term activities and things that have to be done. Okay? So let's start from the current slide, and I have a feeling I know why we're here, but we're on Chapter 4, Integration, 4.2 Area, and we're on Example 7 on page 266, and this is Example 2, so I'm going to step through here and make sure that we're at the right place. We did all this last time. Why was my slide way back there? There was 3A. Yeah, we did that in class, didn't we? Pretty sure we did, yeah. We did all this. Why was my slide way back there? Correct me if I'm wrong, but we've done all this, right? Yeah, we talked about upper sum. Did we do upper sum, lower sum? Inscribe, rectangle, circumscribe?
Maybe we did, yes.
Huh?
Upper sum and lower sum, yes.
I haven't marked that we did. Okay.
Maybe it's just some odd reason not picking up on your bookmark.
What's that?
I said maybe some odd reason it's not picking up on your bookmark, or maybe you just didn't recognize it.
Yeah, I don't know. It may be that it went back to where we started last time. That's probably what happened, and then thought we were starting there again. I don't know. Okay. Pretty sure we did that one and that one. So my memory, we were at Example 7. Is that what you had?
Sounds about right.
Yeah, I'm pretty sure of all that. Yeah, we rushed through Example 6 at the end, I think. So, yeah, we did all this. Goodness gracious. Sorry we're taking all the time. That's why it seems so strange that the marker had us way back at the beginning. But there's one of the reasons is they didn't have anything past Example 5. All right. Whoops, let me get my pen back. Okay. So, Example 7, top of page 266. Any questions before we get started? Okay? And again, please let me know before you leave so I can go over all the stuff at the end of the term that needs to be done, and when and how and all that kind of stuff. Okay, Example 7. Find the area of a region bounded by the graph f of y is equal to y squared. Now, how does that look? Anyone have a clue? We're used to having functions of x. This is a function of y. So when y is equal to 0, f is 0. Now, and in this case, your f of y is x, not y, okay? It can't be, okay? So f of y is x, sort of backwards from what we're used to doing. So when y is 0, f of y is 0. When y is 1, f of y is 1. When y is 2, f of y is what?
2.
Second?
2.
Really?
No, 4.
4, yeah, it's going to be 4. And then when y is 3, f of y is 9, okay? Then that's the x, okay? And don't think I'm going to make 16, but let's see if we can. 8, 9, 10, 11, 12, 13, 14. Almost. When it's 4, it's way out there, okay? So this is what? An upside down parameter. No, not upside down. A sleeping parabola, okay? It's f of x is equal to x squared would be a parabola this way. This is 1 on its side. Now, why didn't I draw the other half of the parabola?
Because dog equal negative y, and you like equal negative
Okay, yeah, because then you're, if you put in a minus y here, like a minus 1, you get 1 again. Is there a problem with that?
Yes.
What?
It's always going to be positive, even then negative.
Okay, well, here's the deal. Remember what the rule for a function is? Vertical line test. And the vertical line test fails if you put the other branch down here, because now the vertical line test function in 2 places is not a function. Right. So that's why we only deal with the top half. Now they only are looking from 0 to 1. I didn't read the problem far enough. I wish I had. Okay, so let me go back and change this. So, going to make a slight change here. 1, 2, 3, 4, 5. This is going to be 1. 1, 2, 3, 4, 5. This is going to be 1. Okay, so that first point is going to be 1, 1. Because we're only going y equals 0 to 1. I didn't read far enough ahead. And this would look something like that. Okay, that's that parabola, but it's blown up in the center. So it says, find the area of the region bounded by this graph, the y-axis. So here's another boundary. Here's one boundary. There's another boundary. For 0 less than or equal to y less than or equal to 1. So you're only going to here. Okay? Actually, I'll draw that in. This is the area we're talking about, this area here. Now, do you want to try to do the x's here? Please say no. Okay, yeah. That would be very much a pain, because then you have to change your y to a function of x, so you can have functions of x here. Since it's then a function of y, do your dy's. Do your rectangles in y's. Okay, so this is your dy. Okay, and this is the x is equal to f of y, which is equal to y squared. So that's in terms of y. This is in terms of y. And what's your area? It's the summation of all those as you go from 0 to 1. So we're doing, I forgot we were still doing this. I can't wait till the next section. Okay, so we're summing the rectangles from 1 to n. Okay, I'll come back to that. N equals, or is it 0? I equal 1 to n. Okay, and then what is your, and since we're doing sums, that's a delta y, not a dy. So what's the area of this rectangle? Well, the length is x, but x is y squared. Okay, and the width is delta y. And we're going to sum all those up from 1 to n. Then we're going to take a limit as n approaches infinity, and let that go forever. Okay? Now, not really, but close. Now, since we're doing our finite ends, okay, not an infinite yet, the finite part here, what we're doing here, let's do what our dy is, delta y is. Remember what that is? The delta y is equal to b minus a over n, right? That's what this is. That's 1 minus 0 divided by however many n's you got. If you break that into 8, that'll be eighths. If it's, 25, it would be 1/25. So this would be 1 over n. Okay? So that's what your delta y is. Now we got to figure out what our y is. Okay? Well, the y at 0, of course, is 0. And at any y up here, this is the y up there is, let's just do what we got so far. This is the limit as n approaches infinity of the summation I equal 1 to n, and the delta y is 1 over n. Okay, that's that part. Now, here I is equal to 0. I is equal to 1, that first little delta y. Then here it's I is equal to 2, 3, and you're counting forth the i's until they get to n. So what your y value is, and here are Catherine and Jordan. Got it? Okay. Now, we're on example 7, page 266, chapter 4, section 4.2. Now, before anyone leaves today, let me know a few minutes ahead so I can go over all the end of the term activities we need to do. So I was going to do an announcement at the beginning, but then people coming in later, I'd have to repeat it over and over. So let's just wait till the end when we have maximum number of people here. Okay. Now, your position here, wherever you are here, okay, this is going to be your y value here, okay? And this y value here is going to be 0 plus however many increments you have, which is 1 over n, okay, from 0. So basically, let's just say that you were had done, let's see, 5 divisions, because I have them here. There's 1, 2, 3, 4, 5. So your n is equal to 5. Okay? This would be, a value here would be something around 1 over 5, 2 over 5, 3 over 5. Well, that's your i's. That's what you're counting. So this one up here would be, say, 3 over 5. This one would be 1 over 5, 2 over 5, 3 over 5, 4 over 5, okay? So your y value, okay, is equal to 1 I over n. Sorry, I over n. Because however many i's you went up here over n, that's your y value. So, since your y is I over n, this is I over n squared, because you're doing a y squared. And Daniel's here. Okay. It's shaping up to be a decent class today. All right, so there is your limit. Because the n's are just numbers, you decide we can do the limit as n approaches infinity of 1 over, see, this n is squared, that one is just to the first power, so that would be 1 over n cubed times the summation from I equal 1 to n of I squared. That's what it boils down to. Well, if you go back to the beginning of this section on page, not absolutely the beginning, very close to it, 259, you'll see these summation formulas. And I squared is n times n minus 1, n plus 1 times 2n plus 1, all divided by 6. Well, I'm going to pull so this will be the limit as n approaches infinity of 1 over n cubed. But you got to divide it by 6 there, so let's pull out that one too, the 6 as well. And this will be Nolan here. Okay. And here you go from the summation to what the summation value is, and like I said, I pulled out the 1 over 6, and we are left with n times n plus 1 times 2n plus 1. Okay? That's what the I squared is. Okay? The summation of the I squared turns out to be that. Now, let's multiply those things together and see what we get. These two multiplied together, so this will be the limit as n approaches infinity of 1 over 6n squared times n times, that would be 2n squared when you do the first term, plus 2n plus n, that would be plus 3n, and then you got a plus 1. Okay? So then multiply the n across there, and you have the limit as n approaches infinity. N approaches infinity. I can't write today. I'm sorry? Okay. I get what you said.
The symbol, what's the symbol called?
The E.
What's the what?
What is it called? The symbol.
Symbols.
The E-looking symbol.
Oh, this one?
Yeah.
That's a summation.
Summation.
Yeah. It's a capital sigma, which stands for sum. Sigma in the Greek
I
alphabet.
know it stands for sum.
Yeah. Yeah. So this is a summation, and we went from this to that. The ends are not, the i's are what's being counted. The end's just a number you choose. You later going to let that go to infinity. So that comes outside of that, and you're left with the summation of I squared. And we got this part from back earlier in the section, page 259, I think it was. They gave us several of those summations, what the formula is. And they just gave us this formula, this over 6, but I brought the 6 out here to put over at the end. Okay, so now we're multiplying these together. And I've done that, but then multiplying n times that, that would be this limit as n approaches infinity of 1 over 6n cubed. That's a cubed. I don't know how it became a square. Okay, and then this will be 2n cubed plus 3n squared plus n. Okay? Now, I'm going to take this up here so I can continue writing. That'll be the limit as n approaches infinity of, now I'm going to put them over that denominator. Okay? And the first one's going to be a 2n cubed over 6n cubed, right? Which would be, the n cubes will go out, and 2 will go into 6. That'll be 1/3. Okay? Plus 3n squared over 6n cubed. that would be 1 over 2n. And n over 6n cubed would be plus 1 over 6n squared. Now, that's something we can take a limit of. Okay. As n is going to infinity, what is this going toward? In other words, n is becoming a very big number. Pick a big number, any big number. Anybody? Pick a big number. Second? 100. Okay, if n is equal to 100, this will be 1 over 2 times 100, that would be 1 over 200. And that's going to be something on the order of 0.005, right? Okay. 100 squared, 10,000. 6 times that is 60,000. And 1 over 60,000 is 0.0008. So a really small number. And as n gets larger and larger, where are these numbers going to? 0. Because the denominator gets bigger, the numerator stays 1, you're getting smaller and smaller fractions. So as n goes to infinity, these two go to 0. So what's the limit? 1/3. Exactly. And that's how they got it. Okay? Now, all right. So that was example 7. Let's see if they have the slide for this next little bit. Whoa, I don't think they do. Finding area by, oh yeah, there it is. Okay. In examples 5, 6, and 7, C sub I is chosen to be a value that is convenient for calculating the limit. Because each limit gives the exact area for any CI, there's no need to find values that give good approximations when n is small. Who cares about when it's small? We're letting n go to infinity, so it gets better and better and better. For an approximation, however, you should try to find the value CI that gives a good approximation for the area of the ith subregion. In general, the good value to choose is the midpoint on the interval, which is halfway between x sub I minus 1 and x sub I. So you add those two together, divide by 2. That's the midpoint rule. Okay? And this is the way we do that. Okay? The area is approximately that. So it really doesn't matter. Actually, any C sub I will work. This one will work better or faster than the others, but any of them will work. So it says use the midpoint rule with n equal 4 to approximate the area bounded by the graph of, let's see, do we have, I think we have room here. The graph of f of x is equal to sine x. So let me try to get that done. Okay. And we'll go 0, and it says the x-axis for 0 less than or equal to pi. Okay, well sine x goes up to 1 at pi over 2 and down to 0 at pi. Okay, this is pi halves, this is 1, and it says with n equal 4. So there's n equal 2, there's n equal 4. So this will be pi fourths, and this is 3/4 pi. Okay, and it said use the midpoint rule to estimate that. And if you are estimating, giving an approximation, and with small number of n's, yeah, this is the better way to go. When you're letting n go to infinity, who cares? Pick the most convenient n, C sub I. Here we're going to do this one. Okay, so here are points. Okay, x sub 0 is equal to 0. This is x sub 1, x sub 2, x sub 3, and x sub 4. Okay, that's our 4. And by the way, our delta x is equal to pi minus 0 over 4, b minus a over n, and that would be pi fourths. We've already shown that, but just to get it down there. Okay, now, if we did this end, that would be a 0. If we did this end, that would be our rectangle. What they want us to do is the midpoint here. What is the function value there? See, that's a better estimate than this, and it's a better estimate than that. That's, you know, this one has, all of it's in error. This one, this part's in error, okay? Here, you just got this part and that part, and they're almost the same, okay? So they sort of cancel each other out. So we want that midpoint. So what is the midpoint? That would be pi eighths, okay? So your c sub 1, if I could get it to right, is equal to pi eighths. Your c sub 2 is equal to 3/8 pi. Your c sub 3 is equal to 5/8 pi. And of course your c sub 4 is equal to 7/8 pi. All right. So what's your approximation? Going to do this function right here. It's the summation of I equal 1 to 4. That's your n. They said do it with n equal 4. Okay? I equal 1 to 4 of your f evaluated at these midpoints. So I'm just going to call that c sub I. And then delta x. Okay? So this will be, let's do those together. Your function is sine of x. F of x is equal to sine x. They said that somewhere in the problem, but I didn't write it down. Yeah, f of x equals sine x. Okay? And we're going to do the center points here. Not the town, but whatever. Okay, so this will be sine of the first center point is pi eighths plus sine of 3/8 pi. All right, Will's here. All right. Again, let me say this. I'm waiting until we get maximum number of people here to make the end of the term announcements, you know, what we need to do, what we're going to cover, how we're going to work it. And because of that, let's wait till the very end of, or wait till before the first person needs to leave. So if you're going to need to leave early, let me know a few minutes ahead so I can make all those announcements so everybody can get to hear them. Otherwise, I'd be doing all those announcements 15 times, okay, as people come in. Well, I'm exaggerating badly. Okay, so this summation would be sine of pi eighths, sine of 3 pi eighths plus sine of 5 pi eighths plus sine of 7 pi eighths. Okay, there's our four sums, and all that's multiplied by your delta x, which is pi fourths. Okay? Now, someone got a calculator? Punch those in. Sine of pi eighths, give me round it to at least 3 decimal points, maybe 4. And you can, well, you don't have to round it. Just punch it in. Okay, we're from the south. We punch stuff. We don't press it. Okay, just do sine of pi eighths plus sine of 3/8 pi plus sine of 5/8 pi plus sine of 7/8 pi equal, multiply that by pi fourths. See what you get. Only one calculator, huh? Oh, no, no. are anticipating these to be pretty good approximations because the midpoint is going to overestimate on this side but underestimate on that side. And the next midpoint here will, right here, it will underestimate here, overestimate here, underestimate there. Next point is basically going to, well, it's going to be here somewhere. Same type deal, so you expect a fairly decent approximation. Has anyone gotten it calculated yet? Okay. We'll just use what the book says. They say this comes up to be approximately 2.052. Yeah, 2.052. Now, this is cheating, okay, to do this to you but this is what we're going to next. If we change that summation to an integral, okay, and we're going from 0 to pi on our dx's, and we haven't done definite integrals yet, but we're coming up on that real soon. Your function is sine of x, okay, and your dx is your delta x, okay? Now that, without the limits there, that's an antiderivative. Does anyone remember what the antiderivative of sine is? It has to do with cosine, but it's not exactly cosine. It's minus cosine x. Okay, now what do we do with those limits? I'm going to put them here, 0 to pi. I'm going to show you what that means. We haven't done this yet, so this is just showing you. That's going to be minus cosine of pi. You put the top limit in there, and then you do minus the cosine of, well, minus, because the thing is minus cosine, minus because that's a subtraction of the minus cosine of 0. Okay? What's that? Next. Okay? Now, what is cosine of pi? Anyone remember? Cosine of pi. Second? Not quite 1. Negative 1. Okay? Remember, cosine function looks like this. It starts at 1 and goes like this. It's 1 at 0, 0 at pi halves, and negative 1 at pi. Okay? So this will be a minus 1, which is 1. Okay? Minus, and what's the cosine of 0? I just said it. Just said it. Where does cosine start? 1, okay? But it's a minus 1 because it's minus cosine 0. And 1 minus a minus would be plus 1 is 2. Didn't know you'd be doing such high-level math today, did you? Okay? And what did we estimate before? 2.052. And this gives us 2. Exactly 2. Not bad. And that's just with n equal 4. If you'd done n equal 8, your 0 is probably would have gone out to here somewhere. So you'd have gotten really, really close in very few iterations. Okay? Don't worry about that part. I just wanted you to see what the real answer was, 2. All right. Homework exercises. I assigned most of these before. I'll only pick up a few more. Any of the odds 5 through 9. Again, all the answers of odd numbers are in the back. All the problems of the odd numbers are worked out tutorial help and worked out solutions for odd number exercises are at calcchat.com. And then number 5 is at calcview.com, which gives you more detail on how to do the problem. So all of those are at CalcChat, 5 through 9, and 5 is at CalcView. Do any of the odds 11 through 15, they're all at CalcChat. None of those are at CalcView. Do any of the odds 17 to 23, they're all at Calc Chat, 21's at Calc View. Do 25 or 27 or both, 25, they're both at Calc Chat, 25's at Calc View. Do any of the odds 29 to 33, they're all at Calc Chat, 33's at Calc View. Do 35, it's at Calc Chat. Do any of the either 37 or 39, they're both at Calc Chat, 39's at Calc View. Any of the odds 41 to 40, either 41 or 43, they're both at Calc Chat, 43's at Calc View. Do 45, it's at Calc Chat. Do any of the odds 47 to 55, they're all at Calc Chat, 49's at Calc View. Do any of the odds 57 to 61, they're all at Calc Chat, 57's at Calc View. And do either 63 or 65, they're both at Calc Chat, 65's at Calc View. All right, there is an exploring concept section here. You don't have to do this, but you might find it interesting. 67 and or 69, they should be at Calc Chat, okay? Then there's 71, that should be at Calc Chat. True false 73, that should be at Calc Chat. There's a writing one, which probably won't be at Calc Chat, but you can check it out, see if you find it interesting or not. That's up to you. There's sort of an applied problem, 77, and if you want to play with that, you can. All right, 79 is a Putnam challenge, so I'll let you decide whether you want to go that far or not. So we are now through with 4.2. So let's go on past this. And since some new people came in, I think it was it Dakota? Yeah. Okay. Now, let me say this again. Before anyone has to leave today, let me know a few minutes ahead so I can go over all the stuff that we need to be sure we cover before the end of the term, that we take care of, that you're aware of. And here's Tyler. So let me start that over again. Okay. All right. Before anyone has to leave today, please let me know a few minutes ahead so I can go over all the end of the term stuff. When things are going to be due, where I'll be, all that kind of stuff. And we will, I was going to do it at the beginning, but so few people were here, and now they've come in, I would have had to stop and go through it all again. So just remind me at the end. Okay, so let's discard that and go to 4.3. I don't know why it's checked on 4.2. There we went to 4.3. Everything's sort of slow today, including me. I'll wait until I do all the end stuff. Okay. Wow, this is taking forever to open. PowerPoint is such a awkward package. Goodness gracious. There we go. Now it's beginning to figure out what we want it to do. One of these days it'll open, maybe. Yeah. All right, here we go. Let's do the slideshow from the current slide. All right. We're still in Chapter 4, Integration. Now we've moved to Chapter 4.3, Riemann sums. Okay, that's a new name, and definite integrals. And unfortunately, we got a little bit of summation yet to go, the Riemann sums part, but then we'll finally get to the definite integrals, which have the limits on them. So, our objectives here: understand the definition of a Riemann sum. And frankly, we've already been using them, so this shouldn't be too bad. Number 2, evaluate a definite integral using limits. That's what we were just doing, in geometric formulas. And then we'll evaluate a definite integral using properties of definite integrals, which are very similar to the properties of indefinite integrals. So let's start with Riemann sums. Whoa, they start with example 1. Consider a region bounded by the graph of f of x equals square root of x, okay? And the x-axis for x equals 0 to 1, okay? It's shown in this figure. It says evaluate the limit n going to infinity, the summation of I equal 1 to n of f of c sub I delta x sub I. That looks pretty familiar, doesn't it? The very last thing we did with the midpoint formulas, where, I'm sorry, what we're doing in the end of the last section. This time c sub I is the right endpoint, not the midpoint, of the partition given by c sub I is equal to I squared over n squared. And delta x sub I is the width of the interval. What a bizarre c sub I squared over n squared. Let's just take one. Give me an n. Pick up an n. Give me any n.
2.
6? Is that what you said?
2.
Oh, 2. 2 will be fine. 2 will be easier. So if n is equal to 2, no. Yeah, n is equal to 2, then the c sub I will be I squared over 2 squared. Okay? This is really bizarre. I've never seen a book do Riemann sums this way. It's okay, but it's rather bizarre. Okay? It's the right-hand endpoints, and for n equal 2, okay, this would be, and you're doing your counting from 1 to n, so you're only doing 1 and 2. So when the first one would be 1 over 4, and the second one, these are the c sub i's, the second would be 1 over 1. So there you would do just, there would be a half, there would be a quarter. You would do the right-hand endpoint there, and you would just do this rectangle here, and then the next one would be that rectangle there. Okay, rather bizarre. Let's go to 4. Then you would do 1 over 16, 4 over 16, which would be your 1/4, 9 over 16, which would be out here somewhere, and then you'd be back to 1 again. So what this is doing is taking very small increments here, and they get bigger as you get closer to the 1, which is, like I said, a really strange way to do a Riemann sum, to use that as your C. I've never seen that used as a C before. But that's what you're doing. So the summation of the one you gave me was 1/4, so that would be the square root of 1/4, which would be 1/2. Yes.
I don't mean to interrupt you, but I got some I got some things I gotta go pay and open at 9 o'clock. I was gonna ask you what you had to say to the whole class.
Okay, you want to hear the announcement time? What you're saying? Okay, I think we got a pretty good number here. So let's do a timeout on this. We'll come back to this, and let's do go over the end of the term stuff. Now, I'll start with my sad song. Okay, we have been involved until yesterday afternoon with doing our planning hearings, which basically is to tell the departments everything we've done in the past year, how we met the plans we had made last year, how we fulfilled them and stuff like this, gathering all the documentation. A huge endeavor. I'm not going to say waste of time, but endeavor. Okay, I said it, didn't I? Okay, sorry about that. Okay, so we have been tied up. I have been for at least a week and a half. That's almost everything I've done. As a result, this is how many papers I've got to grade. These have come in the last week and a half. So I have had 0 office hour time to do any of that. And even when I'm home, over the weekend when I had spare time, I was doing stuff for the planning hearing. So I'm way behind on this. Hopefully this afternoon from 2 to 6, I'm going to get a good start on this, okay? There's a lot to do, but I've got to get it done, okay? So that means Monday, when you come to class, I want all these graded so I can return everything to you that you've turned in so far. Now let's just see if, and some of you may have turned in, have I returned to, well, no. Unless you turned it in the last few days, I don't have all the test 1s or test 2s. I've got some of the test 3s in today. So I'll give them all back to you on Monday. That means I have to have them all in before Monday, okay, or by the beginning of class on Monday. So once I return the papers to you, I can't accept new papers, okay? Otherwise, the answers are out there, and someone who didn't do the work might see the answers and get a real good score, and those that did do the work didn't get as good a score. That's not fair. So I've got to return these to you Monday, so get your stuff into me. And if you want to get it to me before Monday, fine. And so let me go over where I'm going to be and when I'm going to be there, okay? Today, I'm here on this campus all day long, okay? So I have a class right after this one that ends at 1:40. So from basically 2 o'clock to 6 o'clock, I'll be around my office, somewhere around my office, so you can bring anything to me then. And by the way, okay, I'll get to that in a second. Okay, tomorrow I'll be on this campus teaching my classes as normal from 7:45 in the morning until 3:30 in the afternoon. At 3:30 I go to the Birmingham campus, Birmingham East campus, in the Ethel Hall Health Professions building in room 103. So if you do want to turn in something then, I have office hours there from 5:30 till 6. So I'll be in that room from 5:30 to 6 tomorrow. I'm teaching from 4 to 5:30. So you can bring stuff, but I can't interact with you at all, but I'll be there. Okay, Monday, I'm back here. We have classes. Second. That's Ethel Hall Building 103. Okay. Then, and that's my office hours there are 5:30 to 6. Okay. But I'll be teaching there from 4 to 5:30. 4 to 5:30. So you can bring stuff then, but I won't be able to stop to talk with you about it. But 5:30 to 6, I would be able. Okay. Now, Monday, back here, teaching this class, my next class, and then I'm free from 2 to 4. But I've got to have everything in before Monday. So, if you can't get it to me, and say you want to bring it in Thursday, but it's after 3:30 when I left to the other campus, you can take it down and slide it under my door. Or if when I'm in class tomorrow, you want to give it to me, but you don't want to interrupt class, does everyone know where my office is? Here's where we are right now, in this room here. Go out the door, take a left, go down this, there's a half flight of stairs right there. Go almost to the end of the hall. The very last door on the left is the stairwell. The one right before that is my office, 265. There's a mechanical room just like this one right here, and I'm in between the mechanical room and the stairwell. Across from the orientation classroom, 256. The numbers here are strange. So my office is 265. You can slide anything under my door, and as long as I have it before Monday morning, that's great. Yes?
Do you know when this building closes, like when classes end?
At night?
Yeah.
I don't know what time. I know I was here until after 9:15 on Monday night, getting ready for that thing, and the building was still open then. Last night I was on Birmingham campus, so I know it's open after 9. I don't know how long after 9. I'm guessing till around 10 because I think classes usually go till around 10. But I know it's open past 9. Okay? Okay, so you can get stuff to me, and if I'm not here, slide it under my door, 265. Not this door, okay? Yeah, they'll come in and someone pick it up or something. So it's my office door, 265. So get stuff to me before Monday. At Monday, I've got to return all these things to you. Okay? Now, Your research papers. Now, a few people have turned them in since I have it graded, but so far, the ones graded, only 3. Okay, I know I have some more that have been turned in. I just don't know how many. So please get those in. They're due Monday. Okay, so get those to me by Monday. Your tests and stuff before Monday, because Monday, first thing in class, I'm returning those. I can't accept them after that. The research paper I'll accept anytime Monday. If you don't get it to me on Monday and it's Tuesday, Wednesday, or Thursday, you're going to be losing points. I will accept it, but you'll be losing points. Okay? So please get it to me if you can by Monday. The test I need before Monday morning when class starts, the research paper anytime Monday. Okay? Now, I'd rather have it today or tomorrow, but slide it on my door or whatever. All right, here's another thing. I just found this out yesterday. My last class yesterday, they told me this. I asked earlier, various classes, maybe even this class, have you seen anything about student course evaluations? And all the answer I was getting was no, no, no. And a lot of times they don't do them for something. But then, second,
have you sent them out already?
I haven't sent them. They have. Okay, student course evaluations are now available. That's what my last class told me. They got an email last week, they said, that those are available. Okay? Please do those. Okay? And I count the summer ones just as important as I do fall or spring. Fall or spring, we have all Lawson students. In the summertime, a lot of you are not Lawson students. You are transient students. I want to know what you think as well. Now, I'll never know who said what. Okay? Never. They won't let us know that. And I don't want to know that. I see the composite. So please do the student course evaluation. Those are very, very helpful for me in figuring out what to do better, but also just so we get a good measure. Okay, so please do the student course evaluations. And those are open now, and they'll be open at least through finals and probably a little after finals. All right, so Monday at the end of class, I will give you the last test. Okay? Now, I need it back either Tuesday, Wednesday, or Thursday. Okay? Because grades are due in Monday at noon. Okay? Now, if you can't get it to me, and let me tell you where I'm going to be next week. Okay? I went through Monday. Monday's a regular day. I have classes till 11:40, and then 1:40. And then I'm here till 6. Tuesday, I'm here from 7:45 in the morning until noon in my office. No classes, 7:45 to noon. At noon, I've got an exam in this room, okay? And it'll go approximately 12 to 2. I doubt if they'll take that long, but yeah, I'm going to give them at least that long to do. And once it's over, I'll be back in my office. Okay. Second?
Is that Monday?
That's Tuesday. Monday is a class day for us, just as all other Mondays. I'm in class basically from 8 until 1:40, and then in the office from 2 to 6. Somewhere in between 1:40 to 2. Okay. Usually up here doing stuff. All right. So Tuesday, no classes from 7:45 until noon, giving a final from noon till 2 approximately. In the office again from 2 to 3:30, but office down there, 265. And then at 3:30, I drive to the Birmingham East Campus again, same room, Ethel Hall Building, room 103, and I'm there from approximately 4 to 6. Not teaching. That's for those students who turn in their finals. Okay? So I'm there from 4 to 6. I'll be grading papers like crazy. Okay? Wednesday, completely free. I'll be here 7:45 in the morning until 6 o'clock in the evening. In my office or somewhere near my office. So that's time to bring your finals. Okay? Thursday, just like Tuesday, except there's no final that day. I'm in the office from 7:45 in the morning until 3:30 in the afternoon. At 3:30, I go to Birmingham East Campus. I'm there from 4 to 6. So, please get me the stuff by then. If I don't have the stuff, and if you can't, go to the Birmingham East Campus, say Thursday afternoon, 4 to 6, or even 3:30 to 6, you want to slide it under my door, that's fine. When I come in Monday morning, I'll have it there, I'll grade it, and get it done. But I have to have everything in by the end of business on Thursday. Okay? I'll try to make the finals a little bit shorter, and hopefully you'll be able to get that done. Okay. Any questions? Anything I left out? I think I covered just about everything. Okay? Now, yeah. So let's go from there. All right. Let's get back to, seems like there's one other thing. I don't remember what it is now. If I think of it, I'll say it later. Listen to YouTube. All right. So this is a weird way to express the C sub I. Okay? But that's what they ask us to do. Okay? And let's do that. Take the limit. This being our C sub I, our function square root of x. Let's go from there. Okay? The point is, the subintervals do not have to have equal widths. Before we were doing delta x is equal to b minus a divided by n. This is saying, no, they don't have to be equal widths. They could be anything weird like that. That's probably why they did it, okay? Is to be weird, okay? So the width of the ith subinterval is the width of it is the ith subinterval would be, okay, if this is the beginning, let's go back. Okay, something to do. The ith subinterval would be, say, this one right here. Okay? So the width of that will be this value minus this value. That would be the width. So the ith subinterval would then be, since the C sub I is here, the width would be the ith subinterval would be I over n, okay? So that would be at I squared over n squared minus I minus 1 squared over n squared. That would be your delta x. Weird delta x, for sure. Totally strange delta x. Why in the world they do this? So let's do the math here. This becomes I squared minus 2I plus 1. Okay? But you're subtracting that, so you have I squared minus I squared. That goes to 0. And then the minus 2I here, minus here makes it plus 2I, and then the plus 1 here becomes a minus 1 because of that, over n squared. So that goes to 0, so you have 2I minus 1 over n squared. Okay? And that's what they got here. Now, so the limit is n goes to infinity of the summation of I 1 to n of f of C sub I, delta x of I. Here's your delta x of I. Here is your f of C sub I. F, remember, was square root of x, okay? And your x is going to be, remember we said, it's going to be I squared over n squared, okay? So, weird but true. And actually this choice does make some sense now because that's easy to evaluate. It's going to be I over n. So that's going to be, let me get my pen back. This is going to be the limit as n approaches infinity of summation I equal 1 to n, and the square root of I squared over n squared is just I over n times 2I minus 1 over n squared. Okay? So what will that be? The limit as n going to infinity, summation of I equal 1 to n of 2I squared minus I over n cubed. Okay? All right. Now, I'm not going to do all those calculations, but you know how to get them. Go back to that page 259 and get what I squared is, double that, minus I, do that. Here's how they do it. That will be, this is what I got so far. I was right there. The limit is n goes to infinity of 1 over n cubed times the integral, the summation I equal 1 to n, 2I squared minus I. That's where we were. Okay, now plugging in what those are, limit is 1 over n cubed, 2 times, this was what our I squared was. Remember, we just did it in the last problem. N times n plus 1 times 2n plus 1 over 6. And the I here, now this 2 is only in front of this part, minus the I is n times n plus 1 over 2. That's all times your n cubed. So we multiply this out. And if you remember, we did that before. This was 2n squared plus 3n plus 1. Multiply that by n. That's 2n cubed plus 3n squared plus n minus n squared plus n. Well, this is over 6. That's over 2. So you got some math to do, but it's just math. It's just not even algebra, it's just some math to do. And when you do all that together, subtracting off and whatever, and just to see, the 2n cubed over 6, okay, let's just leave that 2n cubed. Okay, you got it 2 times, that gives you 4n cubed. So n times 2n, that's be 2n cubed times 2 would be 4n cubed. That's there. There's no n cubed over there. Your n squared terms would be n squared here. When you multiply this times 1, and when you multiply this times 1, you get 2n. So that would be n squared plus 2n squared. That would be 3n squared times 2 would be 6n squared. I'm moving something out there. No, I'm fine. 2n squared, 3. Well, I'll take their word for it that they did it right. It looks like they may have dropped one, but oh no, because they got it over 6. Okay. This, remember, is going to be a 3n squared because you got to get 6. Multiply this by 3 and that by 3. So this would be. Let's go back to this again. N squared plus 2n squared. All right. 2n squared. 3n squared. Double that is 6n squared. Minus 3n squared. That's how you get your 3n squared. And then for the n part, that would be n times 1 times 1. That would be n. That's the only n you get here, and here you get a minus n. Now, but this is 2 of those. 2 of those minus 3n, okay? So that gives you your minus n. So they did do it right, over 6n cubed. All right, just like we did before. Again, that was just mathematics. It's not even. So this will be the limit as n approaches infinity, and let's break it down like we did before. That would be 4n cubed over 6n cubed, which is 2/3, plus 3n squared over 6n squared is 1 over 6n cubed is 1 over n, minus 1 over 6n squared. Well, that goes to 0, that goes to 0, as n goes to infinity, so your limit here is 2/3. Okay? Now, I think I need to erase that so we can read their writing, and that gives you that exactly like we did, and the limit is 2/3. Okay. Now, why they took us through that is just to show you you don't have to have even intervals like we did before. Okay? So we know that the region shown in figure 419 has an area of 1/3. We did that in the previous problem. This is 2/3. Well, what do we have? A block of 1 times 1. So the total area is 1. The area of the region bounded by the graph of x equal y squared, which is what we did before, and the y-axis, that was 1/3. The one we just did is basically 2/3. It's the same as the function y is equal to square root of x, 2/3, so that adds to 1 times 1 is 1. So I'm not sure why they did that, but it's fine. Okay. Now, because the square bounded by 0 to x going from 0 to 1, y going from 1, or 0 to 1, has an area of 1, you can conclude that the area of the region shown here is, has an area of 2/3, which is what we just calculated to be. The subintervals, and I keep saying this, the subintervals do not have to have equal widths. Okay? Done. We've said that. They said it again. They don't have to be this one, but they just don't have to be equal widths. Okay? This agrees with the limit found in example 1, even though the example used a partition having subintervals of unequal width. The reason that particular partition gave the proper area is that as n increases, the width of the largest subinterval is also going to 0. Because if n is going toward infinity, no matter how big that last subinterval was, it's still getting smaller and it's going to 0. Okay? That is a key feature in the development of definite intervals. Okay? It was before, it still is. In the definition of a Riemann sum below, and this is where we introduce this, note that the function f has no restrictions other than being defined on the interval a to b. Now, what do we mean being defined? It just, every value has a value. Okay? So this means you could have discontinuous functions as long as every value on the a to b produces a function, a value for the function. So here's the definition of a Riemann sum. Let f be defined on the closed interval a to b. It means a and b are included and everything in between. Now let the delta be a partition of a to b given by a is your x of 0, and then you have some x of 1, x of 2, x of 3, x of 4, x of n minus 1, x of n, and that x of n is going to be b. So any partition here, they don't have to be equal widths, okay? Where your delta x of I is the width of the ith subinterval from x of I minus 1 to x of I, okay? If c sub I is any point in that ith subinterval, okay, then the sum of those summation I equal 1 to n of f sub c sub I, delta x of I, as I, x of I minus 1 less than c, so sorry I kind of sneezed.
Plus.
Thank you.
Plus.
Thank you. Okay. The c sub I is just somewhere on that interval, delta x of I. That's called the Riemann sum for that function f for that particular partition delta, whatever you want to call it. Delta. Okay. The width of the largest subinterval of that partition delta is the norm. That's the name they give it. Of the partition is denoted by the width of the largest one is that. It looks like a magnitude of a vector symbol, but it's not. It's the norm of that particular partition. If every subinterval is of equal width, then the partition is regular, and the norm is denoted by, just like we did before, b minus a over n. But even if they're not, you just pick the biggest one. For a general partition, which wouldn't necessarily be regular, the norm is related to the number of subintervals of a, b in the following way. Here's what they're doing. This is for the regular thing, okay? So if you multiply this by n and divide by the norm, with the norm being the largest subinterval, then this number is going to be greater than or equal to this ratio here. Because this thing is always going to be So just do the manipulation there. That means the n is greater than that. That's a general partition. Regular partition is that. I'm not sure why they're doing this much detail here, but it's fine. Sorry. Sorry. Poor people at home didn't know that was coming. Okay. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches zero. We've said that before, they're saying it again. That is, the norm of the partition is approaching zero, implies, I don't know what's going on here, the n is going to infinity. The converse is not true. For instance, say let the norm of n be the partition of intervals 0 to 1 given by this thing, okay? Man. 1 over 2 to the n, 1 over 2 to the n minus 1, keep going until you get up here. So that's 1/2 to 1. The norm of that partition is not going to 0 because the norm is 1/2. That's the largest partition, and that's not changing if you increase n. This is making these smaller down there, but it's still going to be 1 over 2 to 1 there, so that's going to be 1/2. And again, I don't know why they're focusing on this. It's true, but it's not very pertinent, it seems like. It's shown in that figure, or what figure? This figure here. For any positive value n, the norm of that partition is 1/2. That's the largest. That's what I just said. So letting n approach infinity does not force the delta, the norm, to approach 0. In a regular partition, those statements are true. Okay? Now, that looks like a good place to stop for a moment. I've got to go clear my head because all this sneezing is really loosening stuff up. So, if it's okay to take a break now, I'm sorry. Okay. I've got to go. Otherwise, I'm going to be flowing like a fountain up here. Okay. So, let me pause this right now. Maybe the AC just came on and got chilled. I don't know. All right. Where we're picking up here is definite integrals, top of page 272. I'm sorry that took so long for me to clear. Not sure I'm completely cleared, but at least better than I was. All right. Now, to define the definite integral, let's go back to limits again. The limit as the norm, the maximum partition in a maximum partition element in a partition is going to 0. That wouldn't work for that one that was 1 over 2n. That wouldn't work. So why even mess with it? As long as that's true, the summation from I equal 1 to n of alpha c sub I delta x sub I, if that has a limit, and that limit is L, to say that limit exists means there exists some real number L that when you, for any epsilon greater than 0, sounds like a good old derivative formula, isn't it? For any epsilon greater than 0, there exists some delta greater than 0, such that for every partition with the del less than delta, that's that delta there, it follows that the absolute value of L minus the limit here, okay, the object of the limit here, is going to be less than epsilon. Regardless of the choice C sub I, whichever C you choose in there, it's going to work in the I subinterval of each partition. That's going to be true if that limit can go to 0, and that limit, the del can go to 0, and that limit exists. Okay? So, the definition of definite integral, if f is defined on the closed interval, a to b, and the limit of the Riemann sums over some partition delta, as long as that the norm of that partition delta, the largest piece of that partition delta is going to 0, then the sum of I equal 1 to n f of c sub I delta I exists. That limit does exist as described below if all that is met. And f is said to be integrable on that interval a to b. The limit is denoted by, and here's where we get our integral. Okay? Before, we talked about an integral being an antiderivative, which it is. Okay? But here we get a definite integral. The limit is that norm of that partition, the largest element of that partition is going to 0 of the summation of I to equal 1 to n of f of c sub I delta x of I. Now, here's what you're doing. The limit as that's going to 0, just like the limit as delta x going to 0 gave you a derivative. Now the limit as your delta, as your smallest increment here, which is your delta x is going to 0, that sum now becomes an integral. Okay? And the limits of that, you're doing this on a to b, so a is the lower limit, b is the upper limit. Okay? So we haven't defined those yet, but I've shown you before. F of x replaces f of c sub I. So the integral sign replaces the limit of the summation. Your I equal 1 to n, that's going from your first, remember back here, way back here. That was a bad example there. But here, your x sub 0, or your lowest x here was a, your uppermost is b. Okay? So that's why the I equal 1 to n, the low i's are down here, the high i's are up here. So that changes to the low i's give you the a, the upper i's give you the p. Okay? Think of it that way. F of x dx. The limit is called the definite integral from f of f from a to b. That's, you're integrating over that entire region a to b, including the endpoints. The number a is the lower limit of integration, the number b is the upper limit of integration. Just like we saw in our intervals. Okay? The Riemann sums were defined for functions with very few restrictions. A sufficient condition for a function f to be integrable on a to b is that it is continuous on a to b. Has to be helpful for it to be continuous. So let's not have any gaps or breaks in it. Okay? The continuity implies integrability. If a function f is continuous on a closed interval a to b, then f is integrable on that interval a to b. That is, the integral from a to b of f of x dx exists. And you can calculate it if it's a continuous function. So let's do this. Okay? Now we already know how to do antiderivatives, so let's do them. Okay? Now, this doesn't seem fair. They're giving you this and then backing you up and taking you through Riemann sums again. Why would they do that to you? Okay? The difference is this is going from -2 to 1, so this has some places where your function is below 0 and some places it's above 0. Now, they're going to show you, in fact, let them do it, and then I'll show you how to really do it. Okay? It's just, the function f of x equals 2x is integrable on the interval from -2 to 1 because it's continuous. Everywhere, not just from -2 to 1, but definitely from -2 to 1. Okay? And if you, moreover, the definition of integrability implies that any partition whose norm approaches 0 can be used to determine the limit. So rather than doing an integral, we're going back to the partitioning. Okay? For computational convenience, let's define the del by subdividing -2 to 1 into n subintervals of equal width, just like we did before. So your delta x of I, which is your delta x, is going to be b minus a, that's 1 minus a minus 2, that would be 3 over n. Okay? 3 over n. That's your delta x. Okay? Now, choosing a c sub I as the right endpoint of each subinterval, that would then mean that your A, which is your minus 2, plus I delta x will be your ith interval. So that's minus 2, that's the first one, plus I times delta x. Well, I times delta x is I times 3 over n. So that gives you your plus 3i over n. Okay? That is your definition for every c sub I. All right? Now, so the definite integral is then the limit as del goes to 0, your maximum, your norm of that partition goes to 0, of summation of I equal 1, alpha of c of I times delta x of I. Remembering what your c of I is and your delta x of I. Okay? So, let's plug those in. The limit as n approaches infinity of, don't get you to that, of I equal 1 to n of that. Same thing we saw before. Okay? Now, so what was our alpha c sub I? Remember, it was 2x was your function. Alpha of x equals 2x. So that's where this 2 comes from. Your c sub I that we did a couple slides ago was minus 2 plus 3i over n. Minus 2 was the endpoint. 3i over n was how far you are, the ith interval from that. And then 3 over n is your delta x. Okay. Now, what we're going to do is take care of this first. 2 times minus 2 is going to be a 4. Summation of that is that should be 4 times n. Right? Okay. So we'll take care of that. Then we'll use our formulas. We'll factor out the n squared here. Well, this is minus 4 times 3 over n. So it'll be minus 12 over n. Okay. And minus 12 over n, the limit of that is when it goes to infinity, is going to be 0. Okay? Because it's going to get bigger. So that's not really going to contribute anything. Now, this one is 2 times 3i over n times 3 over n. That would be 6, 18 I over n squared. And then we're going to fiddle with that. What we have to do, pull out everything else, and you're left with just an I. So that's where they're going. Let's see how they do it. Okay? So what they did first, this is fine, they pulled out the 2 times 3 over n, because that doesn't have any I in it. The 2 doesn't, 3 over n doesn't. Only this part does. So factor out the 6 over n. So that's on the outside. Not on the outside of the limit, because that's got the n in it. 6 over n is inside this, outside the summation. So now we're doing that. Okay? So let's do that. And that would be minus 2 times the summation of 1. Okay? We've already talked about what that is. And the other part is 3 over n. Okay, so you see what we're doing. They break this into 2 sums. Sum of this, okay, plus the sum of this. Well, the 3 over n is not part of that, so that comes on the outside, and it's just be an I left. So that's how they got that. Now, from our rules, limit is equal to 6 over n. That's there. This is going to be minus 2 times n, right? Well, summation of 1, I equal 1 to n, that'll be n plus n plus n plus n. It's n times 1, so it's n. So minus 2n, that will give you that part. 3 over n times the summation of this, and that, if you remember, is n times n plus 1 over 2. Okay? From the table from before, yeah, n plus n times n plus 1 over 2. So this is minus 6 over n times minus 2n plus 3 over n times n plus n times n plus 1 over 2. So let's do the math, okay? this will be n squared plus 1, n squared plus n, and let's pull out the half here. So 3 halves, n squared plus 1, n over n, and then we'll multiply that by this. So we're going to do all this in one fell swoop here, I think. This gives you the minus 12. Okay? This gives you, like I said, you have 3 halves times 6. And if you do this part, there's just so many little pieces here. Let's do this times that would be 18 over n squared. Divided by 2, that would give you 9 over n squared. Okay? This gives you an n squared. That gives you an n. Okay? So 9 over n squared times n squared. The n squared go out, that gives you the 9. And the last one gives 9 times 1 over n. That goes to 0. Okay? So the limit here is minus 12 plus 9, which is negative 3. Okay. And that's exactly what they got. Now, because that definite integral is negative, it does not represent the area of a region. Okay? If you think about it, areas can be negative. Definite integrals can be positive, negative, or 0. Okay? And what happened here is, like I said before, part of this region was less than 0, part was above 0. Okay? So what we did the negative area here plus the positive area here. This is bigger than that, so it came out a negative number. Okay? For a definite integral to be interpreted as an area, the function f must be continuous and non-negative on a to b. This was not an area. You can think of that as a negative of this area plus that one, and of course the negative of the area is greater than 3. Okay. So here's the next theorem. Definite integral as an area of a region. If f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equal a and x equal b is, rather than having to do a sum, that area is now the definite interval, a to b, requiring that this f never be negative on that. Okay? This works quite nicely. Okay? Interval from a to b. Okay? The integral of the f of x from a to b will give you this area up here. Okay? That's what definite integral gives you. You could not extend the a out to here because this part is less than 0. You can go as far that way as you want to because that stays positive. Okay. As an example of theorem 4.5, the one we just said, consider the region bounded by the graph of f of x equal to 4 minus x squared. There it is. The x-axis is shown there because f is continuous. That's one thing. Non-negative, as long as you're in the interval from 0 to 4. You can't be outside that because it goes negative on either side there. You can calculate the area there. Now, they still haven't told you how to do the limit shift. And if they're going to do a Riemann sum, I want to puke. Okay, no. Okay. They're just saying you can do that. Okay. You can evaluate a definite integral in 2 ways. You can use that limit definition. I'm sure you want to use that your whole life, don't you? Or you can check to see whether a definite integral represents the area of a common geometric region, such as a rectangle, triangle, or semicircle. Or those are our only 2 options. No. Okay? Oh man, I can't believe they're taking us through this. Sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. What is that in functionality? F of x equals 4. It's a constant function. X equals 4. And if you're going from 1 to 3, 4 from 1 to 3, that's going to be a rectangle. The height is 4, the width is 2. 4 times 2 is 8. 4 times 2. Yeah. Okay? That's going to be that one. You can get that very easily from there. Okay? F of x is 4, constant function, going from 1 to 3. That's a rectangle. 4 times 2 is 8. Okay? Let's go back to the next one. This is the integral from 0 to 2 of x plus 2 of x plus 2. Well, x plus 2 is a line with slope 1, y-intercept 2, okay? You're going from 0 to 3, x equals 0, that's your y-intercept, so you're going from 2 up to there, and that's basically going to give you a trapezoid, okay, like this, from here to there, and what you do is take that area, this is what you're looking for, but if you flip that over the upper part, that's, and then take half of that, you're going to have a rectangle, and take half of it, you get the area of the trapezoid. So here's how that looks. This region is a trapezoid, altitude 3. Altitude 3. Okay, they're doing that being the altitude, I don't know why. Parallel bases of x equal 2 and x equal 5. Because this is 3, that goes up to 5, and this is 0, it only goes to 2. And the formula for a trapezoid is 1/2 the height, they call it the altitude, 3, times base 1 plus base 2. Okay? In other words, you do the base 1 here. When you flip that across here, you're doing that base there, so that would be 2 to 7. And that would then be twice the area. Half of that would be this. So that would be area of the trapezoid. Base 1 plus base 2, that's 2 plus 5 is 7, times 3 is 21, and half of that is 21 halves. Why are they taking you through all this? I'm not sure. Okay, let's go to the next one. This is the integral of the square root of 4 minus x squared from minus 2 to 2. If you were to graph that, here, rather than graphing, think it through. Let's call this our f of x. And f of x is typically y, right? So y is equal to the square root of 4 minus x squared, right? Square both sides. Y squared is equal to 4 minus x squared, right? Add x squared to both sides. And you get x squared plus y squared is equal to 4. Any idea what that is? Anybody? X squared plus y squared equals 4? Say again? A circle of radius? No. 2. X squared plus y squared equals r squared. So the square root of 4 is 2. So that's the circle of radius 2. Well, what have we described here? We're going from the positive square root of that, so we're doing the top half of a circle. So that's a semicircle of radius 2. 2 over here, 2 over here, half of that radius 2. So what is it? So this is 1/2 the area of a circle of radius 2. And what is the area of a circle of radius 2? Pi r squared. So it's 1/2 pi r squared, where r is 2. So that would be 1/2 4 pi. That would be 2 pi. All right, let's see if that's how they did it. Sure enough, when they drew it like this, it looks like it's a semicircle, And indeed it is, and they do half of that. Sure enough, that's too high. The area under there is too high. Why are they taking you through all this? I do not know. But that was example 3C. The variable of integration in a definite integral is sometimes called a dummy variable. Not because it's dumb. It just, in a definite integral, you're going to lose it anyway. So it doesn't matter what you call it. Okay? Because it can be replaced by any other variable without changing the value of the integral. For instance, the integral, definite integrals, integral from 0 to 3 of x plus 2 dx is the same as the integral from 0 to 3 of t plus 2 dt. It doesn't matter what you call the variable, you're doing the integral of that. They have the same value because they plot the same thing. It's just like you can rename your x-axis anything you want to. It could be x, it could be t. You usually don't want it y because that's what the y-axis is, but it could be anything you want to. It could be stickman, anything you want it to be, okay? So therefore, it really doesn't matter what you name it. That's why it's called the dummy variable. Now, that leads to properties, it really doesn't, but that's what we're going to do next, properties of definite integrals. Okay. The definition of definite integral of f on the interval from a to b specifies that a has to be less than b. Because if you're going from a to b, you expect a to be less than b. Now, however, it is convenient to extend the definition which either a is equal to b or a is greater than b. Okay? Now, geometrically, the next two definitions seem reasonable. Okay? And indeed, they will be true. For instance, it makes sense to define the area of a region to be of 0 width. It's going to be 0. If it has a finite height and 0 width, 7 times 0 is 0. 85 times 0 is 0. 4,585,815 times 0 is 0. Okay, so it doesn't matter what as long as you have a finite height, if your width is 0. So therefore, if a is equal to b, that's going to be 0. The definite integral is going to be 0. Okay? So, here we go. Definition of two special definite integrals. Okay? If f is defined at x equal a, then the integral from a to a of f of x has got to be 0. Because your width here, delta x is going from a to a, the width is 0. So as long as this is a well-defined function, that's got to be 0, always. Now, here's the other one. If f is integral on a to b, then an integral from b to a of f of x dx, okay, if a is less than b, and you're doing this, then basically what you're doing is a negative area, you might think, okay? Because you're going from the high side to the low side, okay? So what you do to reverse that is negate this and go from a to b, the lower value to the upper value, and that's going to be the same. So this is going to give you a negative value, so the negative of that will be that value. So hopefully those make sense. So let's do example 4. Oh my word. 4a is pretty easy. What's that? Integral from pi to pi of sine x dx. Yeah, those are the same values, so that's equal to 0. The width is 0. You're going from pi to pi. You're not going anywhere, so the width is 0. This one, tell me what that is. Yeah, that'll be negative the integral from 0 to 3. Reverse your things, change the sign of x plus 2 dx. Well, we did that just a few minutes ago. That was that trapezoid. and that came out, what, 21 halves, I believe it was. Okay? So this will be a negative 21 halves. Okay? It just negates this one. Okay? So let's clear this. This is just thinking through. I wish they'd get on to really doing the integrals. Okay. Because the sine function is defined to x equal pi, it has a finite value there, and the upper and lower limits of integration are equal, it's got to be 0. Okay? And this one, the integral from 3 to 0 of x plus 2 dx is the same as that given in example 3b, except that the upper and lower limits are interchanged, so you just change them back, putting a negative in front, and we already calculated that to be negative 21 halves. Negative the integral of 21 halves. Okay? Now, okay. Continuous and properties of definite. In this figure, the larger region can be divided at x equals c into two subregions whose intersection is a line segment. What? Okay. The larger region here can be divided at x equals c into two subregions whose intersection is a line segment. So I think they mean this dotted line here is that line segment, which is the intersection of this region and that region. It's just that line they have in common. Best I can figure what they're saying. Because the line segment has 0 area, it follows that the area of the larger region is equal to the sum of the areas of the two smaller regions. Oh, wow, what a surprise, okay? If this region is made up of this and that, then the area is that area plus that area. Yeah, I think we can handle that, okay? So the integral from a to c of f of x dx plus the integral from c to b of f of x dx is just going to be the integral from a to b of f of x dx. If these two are the same, then you can just combine them, okay? So this is the additive integral property. If f is integrable on three closed intervals determined by a, b, and c, three closed intervals a, b, and c, then the integral from a to b of f of x dx is the integral from a to c f of x dx plus the integral from c to b of f of x dx. Now, the main application of this would be if you have a discontinuity. Okay? And say f was up here, but then changed over here. Do your c here, right at the dividing line, do the area under here and the area under here, and you can do it. So this enables you to then do integrals over a discontinuous function. Just make the discontinuity, that point, be the dividing line. And then you can do that. That to me is the most, okay, so let's see, example 5 is that, that's the next one. So, this is not exactly a discontinuous function, but it is a piecewise defined function. The absolute value of x is defined one way when x is negative, and defined another way when x is positive. It's minus x from 0 for negative x's, and it's positive x for positive x's. Okay? Because absolute value always has to be positive, and since between these values x is negative, so you negate that and you get this. So this is a good way to do, even if it's not a discontinuous function. If it's a piecewise defined function, this does well too. Now, and again, this is a rather bizarre. If you draw your graph, and I wish they get on to doing the real calculus here, okay? You're talking about this area plus that area, okay? Well, this is exactly half of a square, right? It's a triangle. the base is 1. This is going from -1 to 0, and the height is 1. Okay? So this is 1/2 of a square. So this would be a 1/2. This would be a 1/2, and that's equal to 1. Okay? Or those two add together to be a full square. Okay? So, again, why are they dragging us through all this? 1/2 plus 1/2 is 1. Okay. Almost as good as 1 and 1 is 2. Now, more properties of definite integrals. If f and g are integrable on a to b, k is a constant. Now remember what it takes for them to be integral? If they're both continuous there, we know they're integral. Okay? They have to be defined at all values. Okay? And k is some constant, then the functions kf and f of f plus or minus g are also integrable. And the integral from a to b of kf of x dx, pull the constant outside the integral, the k times the integral from a to b f of x dx. We already said this is integrable, so that has a value multiplied by k and got it. Or if you're adding or subtracting two functions that are both integrable, then you can split them up. The integral of a sum or a difference is the sum or the difference of their integrals. Okay? Just like you would expect, it happens. Works this way for sums, it works this way for integrals. Integral from a to b of f of x plus or minus g of x dx is the integral from a to b of f of x dx plus or minus the integral from g of x dx. Note that property 2 can be extended to cover any finite number of functions. It can be plus or minus h of x, plus or minus k of x, plus any number you have to split it into integral of each one of them, as long as each one of them are integrable. Okay. So here's example 6. And that is the next one here. Oh my word. So what we have is the integral from 1 to 3 of minus, well, they've done it all for you. Okay. This is really interesting. Evaluate the integral from 1 to 3 of minus f x squared plus 4x minus 3 dx. Okay? Using this. Now, they didn't tell you how they got it, but using this, that the integral from 1 to 3 of x squared dx is 26/3, and the integral from 1 to 3 of x dx is 4. Okay? And that the integral of dx from 1 to 3 of dx is 2. Okay? Now, they just told you that was the case. You know this is the case. Integral of 1 from 1 to 3, that's a rectangle, height 1, width 2. Whatever. 1 times 2 is 2. That one's pretty obvious. They gave you the other two, which are both true, but they didn't tell you how they got them. So what would this be? If you break this down, you have minus the integral from 1 to 3 of x squared, right? Plus 4 times the integral of x from 1 to 3. Oh, that's x squared dx. Sorry about that. Of x dx minus 3 times the integral of dx. Would you buy that? Write this down, split it into the 3 different integrals, and then pull the minus sign out of here, and have the integral of x minus the integral of from 1 to 3 of x squared dx, plus 4 times.
What about the signs? Because you took out a negative, shouldn't the other signs change? So you made the first term a positive, shouldn't that plus 4x be a negative and the 3 be a positive?
Well, you change your problem.
Right.
Yeah, that's a different function. It's the opposite of this function. Okay. But then plus 4 times the integral of x dx. So you just factor out the 4, that's that constant, and then factor out the 3, and then you have just the integral. Oops, sorry, from 1 to 3. But they told you what this is. This is 26 thirds. So this is minus 26 thirds plus 4 times 4. They told you that part. Minus 3 times 2. Right? This is, I look at this and say, how is this even calculus? But I guess there's a reason for this. Minus 26 thirds plus 16 minus 6. I'm first going to take care of this and make that a plus 10. Is that okay? Okay. And that would be plus 30 thirds, right? 30 thirds minus 26 thirds would be, it's not negative, 4 thirds, right? Yes? Okay. 4 thirds. So we hope that's equal to 4 thirds. And sure enough, that's what it is. So, all right. Now see how they did it? I'm sure they're going to take a lot more steps than I did. Okay, first they're going to write it over again. That's really helpful. And then they're going to take this by our sum and difference property. This will be the integral from 1 to 3 of minus x squared dx plus the integral from 1 to 3 of 4x dx plus the integral from 1 to 3 of minus 3 dx. Okay? And what we're going to do here is pull out the minus sign, which is going to make that minus the integral of x squared dx from 1 to 3. Pull out the 4, so it's plus 4 times the integral from 1 to 3 of x dx. Pull out the minus 3 and do the integral from 1 to 3 of dx. So they gave you all those parts. That'll be minus 26 thirds plus 16, 4 times 4, minus 3 times 2, and that gives you 4 thirds. They didn't show you how they got it, but they got it. Okay? Make sense? Why are they doing this? They're dragging this out forever, and we still haven't shown how to evaluate one. Okay? One more slide here, I think. If f and x, f and g are both continuous on some closed interval a to b, and 0 is less than f of x, meaning f of x is non-negative, and f of x is less than or equal to g of x, meaning it's non-negative too, for all x's between a and b, then the following properties are true. First, the area of the region bounded by the graph of f and g, no, f in the x-axis, this is f, is always less than or equal to g, and in that between a and b, the area of the region bounded by the graph of f in the x-axis between a and b must be non-negative. Yeah, because f is greater than or equal to 0, so the area's got to be non-negative. Of course, the area is always, Second, the area must be less than or equal to the area bounded by the graph of g, because g was always greater than or equal to x. So it's got to be less than or equal to that. Okay? Yay. Okay. We got it. If f and g are both always positive, or non-negative anyway, and f of x is always less than or equal to g of x, then the integral of f of x is always less than or equal to g of x. Okay. Hopefully that makes sense. So those two properties, if there are two there, it's generalized in theorem 4.8. This is the preservation of inequality. If you want it, make sure you preserve it. If f is integrable and non-negative on some closed interval a to b, then the integral of f of x dx has to be greater than 0. From a to b has to be. If f is non-negative and you're integrating that, the area under that, it's got to be greater than or equal to 0. Now, if f is 0, then it would be exactly. That would be fine. And f and g are integrable on the closed interval a to b, and f of x is always less than or equal to g of x for every x from a to b, then the integral of f of x from a to b is less than or equal to the integral from a to b of g of x. Okay. All this stuff, and we have actually evaluated an integral. Okay, not yet. Okay, I don't know why they're stringing it out this way, but he is. All right, homework exercises here. Do number 3. It's both at Calc Chat and Calc View. Do any of the odds 5 through 9. They're all at Calc Chat. 7's at Calc View. Do 11 is a Calc Chat. Do any of the odds 13 to 21. They're all at Calc Chat. None of them are at Calc View. Do any of the odds 23 to 31. They're all at Calc Chat, and 25 is at Calc View. Do any of the odds 33 to 37. They're all at, 39. They're all at Calc Chat. 37 is at Calc View. And then I would do any of the odds 41. I'd do either 41 or 43. And then I would do 45. And you can think about doing 47 if you want to. That's completely up to you. In fact, 47 is a pretty good problem, I think. Yeah. And then 49 is another think about it. I think that's a pretty good one to look at and think through. 51, you can do that one too if you'd like. That's completely up to you. Exploring concepts, 53 is worth taking a look, and 57, you can look at, yeah. It says describe 2 ways. It's just a description. It's not, you don't have to actually do it, I don't think. Finding values, 59 or 61, either one of those. They both should be at Calc Chat. True false, 63 through 67. So you can do any of those. They should be at Calc Chat as well. 69 is finding a Riemann sum. And okay. You can do that one if you want to. It's giving you the C values to use for doing your approximation of a Riemann sum. That's a summation, not an integral. If you like proofs or want to think about it, you can do 71. That should be at Calc Chat also. You could think about 73. That's a little more of a bizarre thing, so I'm not sure you want to do anything with that. You can give it a look. The Dirichlet is a Dirichlet function. You can look up and see who in the world Dirichlet was, okay? That would be worth a paper topic anyway. How he came up with this function, or why in the world did he come up with the function, that might be a more interesting topic. Finding values, 75. Think about it, 77. You can do these if you want. If you don't want to, you don't have to. But those are both should be at Calc Chat. And then using a Riemann sum for 79. Again, if you find that helpful, go for it. If you find it useful. Let's get out of here and move on. Yeah, we got some time. To 4.4. Finally, folks, we get to how you actually evaluate these things. So everything we were just doing is almost ancient history. I mean, yeah, it's sort of like, how many of you, when you go to take a derivative, go back to your limit formula? No, you just take your derivatives. Same thing here. All that was your limit formula of Riemann sums. That's what the definite integrals are. What we're going to do now is actually figure out how to do them. Okay? So we're in Chapter 4, Integration. 4.4 is the fundamental theorem of calculus. What we're going to do is evaluate an integral using the fundamental theorem of calculus. We're understanding use the mean value theorem for integrals. We'll find the average value of a function over a closed interval. We'll understand and use the second fundamental theorem of calculus. They used to call them Part 1 and Part 2. I guess they kind of call them fundamental and second fundamental. And we'll understand and use the net change theorem. Is there more? Yeah, no, we start with fundamental theorem of calculus. You have now been introduced to two major branches of calculus, differential calculus and integral calculus. At this point, these two problems seem unrelated, but there is a very close connection. The connection was discovered independently by both Isaac Newton and Gottfried Leibniz, and is stated as the fundamental theorem of calculus. Informally, the theorem states that the differentiation and the definite integration are inverse operations of each other, in the same sense that division and multiplication are inverse operations. To see how Newton and Leibniz might have anticipated that relationship, consider the approximations shown in figure 427. Okay. Now, for differentiation, if you're differentiating this function here, you approximate that. The derivative of that is approximating the slope of the tangent line, either at this point, that point, somewhere in between. And what we use to approximate it is the slope of the secant line, which is your delta y over your delta x, rise over run. And that led to dy dx, which is your derivative. Okay? Now, that's the secant line. The tangent line is not that. There's a tangent line. Its slope is dy dx, and I don't know why they still have the delta there, because it's definitely not the same. That line and this line don't have the same slope. Is that what was intended here? I guess maybe I should read more of this, but if you let the delta x get smaller and smaller and smaller, then yes, that works, okay? But not the same delta x is here, okay? So I think that must be what they mean. Let the delta x get smaller and smaller and smaller, and that the slope of the secant line then is approaching the slope of the tangent line, if your delta x is extraordinarily small. Okay. Now, let's look over here for integration. The area of this rectangle is this, and the area under the curve is that. Okay? So the area is delta y times delta x. That's of the rectangle. The area under the curve is if you take smaller and smaller rectangles and add them up, that's your delta y over delta x. You have very small increments of them. So again, you're letting your delta x approach 0. Okay? This is for any delta x. As the delta x is approaching 0 and you add all those up, then you get the area under the curve. So that's a product. This is a quotient. Multiplication and division are inverse relationships. So are differentiation and integration. Never seen it approach that way, but it's a decent approach. Okay? Now, maybe they're going to explain some stuff here. The slope of the tangent line was defined as the quotient delta y over delta x, slope of the secant line. Similarly, the area under a region was defined using the product delta y times delta x. That's the area of a rectangle. So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to have the inverse relationship in the same sense division and multiplication are. Fundamental theorem of calculus states that the limit processes used to define the derivative in a definite integral preserve that inverse relationship. So here is what we got. Fundamental theorem of calculus. This, in many books, we call it part 1. If a function, f, is continuous on the closed interval, a to b, and this is the little f, and capital F is an antiderivative of little f on that interval, then, and this is what I've been wanting them to get to all this time, if capital F is the antiderivative of that little f, remember you can't say that this thing would be capital F of x, you'd always have a plus c with it, remember? When you did the indefinite integrals, you always had a constant of integration. Well, if you have limits of it, then this says it's going to be that antiderivative, but first evaluated at b, and subtract from that the evaluation at a. Okay? Now, what is that saying? Kind of. The integral of a function is going to be its antiderivative. So integrals, derivatives, inversely related to each other. But that's the fundamental theorem of calculus. Many books call it part 1. That's it. That's how you do definite integrals. So all that other mess about, areas and other things like this comes down to this. And it's so much easier to do. It's doing the antiderivatives that we did before we had the limits and just using the limits in this way. Okay? Okay. All right. Next slide is on page, and that slide was too, on page 282. Too much time. Following guidelines can help you understand the use of fundamental theorem of calculus. Okay? Provided you can find the antiderivative of f, which we did a chapter ago, you now have a way to evaluate a definite interval without having to use a limit of a sum. Thank you. Okay? Those things are such a pain in the neck to have to fiddle with. When applying the fundamental theorem of calculus, the notation shown below is convenient. The integral from f of x dx, integral from a to b of f of x dx, is the antiderivative of f of x, which is your capital F of x, remember? But rather than putting a plus c, you evaluate it between those limits, which means f of b minus f of a. So let's do one here. To evaluate the integral of from 1 to 3 of x cubed dx. First, what is the antiderivative of x cubed dx? Anyone remember? I know it was a long time ago. Antiderivative of x cubed.
3x.
And you're taking a derivative. Antiderivative.
So, I know it's something involving a negative in x.
Now, yeah, this one doesn't have a negative. What is it?
Positive. N plus 1.
N plus 1, that's it. And what's your n? 3. So that'll be a x to the 4th. So there's another part. Whereas if you were taking the derivative, you multiply the exponent by the coefficient, divide by the 4. So this is x 4th over 4, right? And put those limits on from 1 to 3. So that would be x to the 4th over 4. That's the antiderivative, going from 1 to 3. So you put the 3 first. 3 to the 4th over 4, minus 1 to the 4th over 4. 3 to the 4th is 81, so that's 81 fourths minus 1 4th. That would be 80 fourths, which is 20. Pretty good. Or you could go back and do your limit. No, please don't even think about it. Okay? It is not necessary to include a constant of integration c in the antiderivative because you've taken care of that with your limits. So in indefinite integration, yeah, you always have to put the plus c. But this one you don't. And here's kind of why. Okay? If you did the f of x plus c, like we used to do, but evaluated from there to there, that would be f of b plus c minus f of a plus c. Here you have a plus c, here you have a minus c, they disappear, it's still just f of b minus f of c. You don't need the plus c in the definite integral. Ever. Indefinite integrals, always. Definite integrals, never. So let's do something. Evaluate each of the following definite integrals. Oh, man. All right, you tell me what to do. Whoa, I got to get my pen back. Where is my? So there it is. Okay.
Would that be x cubed over 3 minus 3x?
All right, excellent. The antiderivative of that would be x cubed over 3 minus 3x. Evaluate that from 1 to 2. And that would be what?
It would be, so it would be 2x cubed.
Say again?
It would be 2 cubed over 3.
2 cubed over 3, which is, I'll write it down that way. 8 over 3, I'll write it down that way. 8 over 3 minus 6.
Which is,
minus, let's put this in parentheses. Say again?
26 over 3.
A little bit louder.
I was just doing the first when you subtract 8 over 3 from minus 6, that'd be 26. No.
Okay, wait, don't worry about that yet. Let's go on and do the second part. That's the upper limit. You put those in. Now subtract from when you put the lower limit in.
1 over 3.
1 over 3
Minus 3.
minus 3. Okay? Now, that would be 8 thirds minus 6 minus 1 third. Plus. Don't watch those signs. Okay, plus 3. Okay? And that would be 8 thirds minus 1 third would be 7 thirds minus 3. Minus 6 plus 3 is minus 3. Well, that would be 7 thirds minus how many thirds is 3?
3.
Huh?
3.
How many thirds is 3?
3.
No, it isn't. 3 thirds is 1.
Oh, would it be 9?
9! It would be 9. So this would be?
It would just be
negative 2 thirds. Okay, the calculus are doing pretty well. It's the math that's getting you, right? Okay. We think that is going to be negative 2 thirds. Now, it took a lot of room to do that, so I'm going to erase it. But remember, that's what we think it is, right? Let's do the B part. Okay, how would you approach that? You tell me.
Trying to do the antiderivative. What about that square root? Can we get rid of it somewhat, or do we just keep it?
That's my question to you. What do you do? How do you approach that? Anybody?
Square.
No, let's not do that. We have to use this one.
You can make it x to the 1/2.
Exactly. Okay? Change the form. Okay? Now, also, before I do even that, I want to pull that 3 on the outside. There's no reason to haul around that 3. Inside the integral, you can pull it on the outside. Remember, that's one of the rules. That's going to be 3 times the integral from 1 to 4, and then change the square root of x to x to the 1/2 dx. Okay, now with that in mind, you got 3, and what's the antiderivative of x to the 1/2? Anybody? Antiderivative of x to the 1/2.
That would just be
X to the what?
x to the 3/2.
3/2, yes.
Divided by, I want to say 2 over 2.
Okay. Divide it by 3/2. Divide it by that very thing, just like we did, is x to the n over n. Okay, so that's over n. But dividing by 3/2 is the same as multiplying by 2 thirds. right? Dividing by 3/2 is the same as multiplying by 2/3. Okay? And now we're going to evaluate that. If I can get the line to draw, why won't the line draw? It's going to all draw 3 times or 7 times. Why won't the line draw? There, we got it. There, I told you it was going to draw a lot. Okay? Evaluated from 1 to 4. So what's that going to be? Well, before I do any evaluation, let's do easy stuff. The 3's can cancel out, can't they? Okay? So now we're evaluating 2 times x to the 3/2 from 1 to 4. So that's 2 times. Now, how do you like to do something to the 3/2 power? Second?
Whatever you're called for it.
No, it's raised to a power.
The bottom, make it a negative.
Say that again?
Wait, don't. Wait, you move to the bottom and make it a negative.
It's just the cube root of it.
Okay, yeah, okay, now that's why. It's the cube, it's x cubed, but it's the square root of x cubed, or
No.
the square root of...
Is it x cubed?
Okay, no. The denominator is the index of your radical, and the numerator is the power.
Okay, so it's the square root of x.
The square root of x cubed, or the square root of x cubed. I like to do it that way because it keeps the number small. So what's the square root of? Your upper limit would be 4 to the 3/2 minus 1 to the 3/2. Okay? So this will be 2 times what's... You mind doing the square root first?
Sure.
Square root of 4 is? 2. Cubed is? 8. Minus the square root of 1 is? 1. And 1 cubed is? 1. Okay. So this will be, it's not hard, 7. And that is 14. Okay. I've got to erase this, so remember that one. Okay. Oh, man. We're out of time, aren't we? Okay. Sorry about that. Let's just check those 2 answers quickly. Okay. The first one was negative 2/3. Wasn't that what we got? Okay. And the second one was 14. Yes. So we'll pick up and do the third one next time. Okay. Let me give you a few homework exercises due in this section. That will be, goodness gracious, this is a long section. Any of either 5 or 7, they're both at calcchat.com. And I think you can do some of the odds 9 through 27. And they're all at calcchat.com, 19's at calview. Okay, good deal.
Question. So
Yeah.
Everything else, I'm confident, like, is great. I see that. Then, like, I put 2 answers. Like, this is just that, and then that's 0. I got the 2.5.
Okay.
That's the chain.
Oh, you've just done it.
That's just simple. That's just
Right.
simplified.
Okay.
And my question is for liver problems. When you do that, that's all you do is just take the liver and then plug it in.
I think so, yeah, that was good. Yeah, good deal. All right, good deal. Thank you. Thank you. Oh, plenty to grade. Thank you so much. Okay.
Were you able to bring the final?
Okay, let me see. I know I checked and made sure I had it, but what I don't know is if I have any copies of it. Okay, this is test 4 for 125. That's 3. I'll get there one of these days. There's test 4. Is that my current test 4? I don't think so. it out to make a copy. Yeah, must have, and I don't see it. Let me go back and check these again. Okay. There's my test 3 that was
Have a
critical.
good weekend.
Okay, you too, thanks. Test 3. Test 3. That's it. I just don't see, I only have the master. So let me make a copy of it. We're going to do more than this because I don't even have it. I think I had it in my original, but I can't find the original, the second page of this. But I'll just let you just do this part. The others may have a little bit longer to do. But will you be okay with that?
Yeah, no, that's fine.
You will let me get away with it. Let me let this go.